Good evening to everyone. I'm very glad to be here tonight, and I want to thank Dialog and contest organizers for giving me the opportunity of live this wonderful experience. Moreover, I'd like to express my particular appreciation for the location chosen, the Naxos Gardens, the cradle of Magna Grecia, and as a student of ancient Greek, believe me, there wouldn't be any better place. I come from Uboldo, a little town about 30 minutes from Milan, and I'm 17 years old, so I'm going to start my 5th year at Liceo Classico Stefano Maria Legnani. My school focuses on the teaching of humanistic subjects, in particular Latin and Ancient Greek. Despite the fact informatics is not taught in my institute, my math teacher Roberto Minervini has introduced me to APL language during a one-year-long course. At first, I thought that learning and understanding a programming language would have been a mission impossible for me because of the unbridgeable gap always pictured between scientific and humanistic subjects. Nevertheless, curiosity urged me to take at least a shot, and above all, I didn't want to regret not having tried. During the course, I come to notice that there is an important element in common to both categories of subjects, logic. And in Ancient Greek, logos means word, idea, argument, reasoning. And in my school, it is developed through translation from Greek and Latin, and is the base of philosophy. On the other hand, in informatics, it is essential to find the right and the best function to solve the problems. When I first managed to articulate my first function in APL language, it was as though I finally broken into the world of programming. And I felt the same emotion I felt when I translated my first sentence by Ancient Greek. Then it was like I had opened a connection that allows me to communicate with the ancient world. Now I will be able to communicate with the world of the future. It was only the first step of a hard work, but as Plato said, the beginning is the most important part of the work. And I want to thank also on behalf of my schoolmates, my teacher Minervini, for having taught us APL language and for having introduced us to the programming world with enthusiasm, working together, and with a contagious passion. And I want to say a special thank you to him for having trusted me and proposing me to take part into this contest. Of course, I was aware that high school students would stand little chance against undergraduates, but in my case, something makes the difference. I also want to thank my schoolmates with whom I had the opportunity to collaborate, and we have shared moments of hard work and confrontation, but the atmosphere was always fantastic due to the sympathy that united us, and it was a real joy working together. In fact, it is important to mention how the first step to the solution of each problem, apart from their most technical aspects, is of course their abstract understanding, and discussions and confrontation between me and my classmates were essential to find ideas that were later translated into APL language. Without this moment, I certainly would have never managed to achieve the victory in this competition. And this is why I believe that working together can really help teaching extraordinary results, which could never be achieved by yourself. However, even the help of internet have been very useful. So the contest consisted of 2 phases. Phase 1 had not very articulate problems that could each be solved with a single line of APL code. Phase 2, on the other hand, consisted of 3 sets of problems: bioinformatics, applications problems, and recreational endgame problems of varying complexity. Here I will take into consideration the problems of both phases that I like most and that I found most interesting. However, in some cases, I will explain function a little bit different from those I'd sent for the contest to simplify the exposure. Phase 1, unlucky 13. We have to change every 13 in 12.99 into an array. So this is the function. I obtain a Boolean vector in which 1 corresponds to 13. I multiply the Boolean vector for 0.01, and I subtract from the starting vector the obtained vector. His sum mean has no standard deviation, phase 1. The standard deviation of a population is calculated by taking square root of the average of the square differences of the values from their average value. So this is the mathematical formula. And we have to write a DFN that returns the population standard deviation of its numeric array, left argument. So this is the function. Here I make the average of the value. I make the differences between the values and the average value. I make the square of the differences. Here I make the average of the value that I've just obtained. And finally I make the square root of everything. I'd like my scrambled, please, phase 1. Write a DFN that takes a character vector as its left argument and returns the words letter inverted 2 by 2 except the first and the last ones. So for example, argument becomes agmunet. This is the function. I take the last letter. I remove the first and the last letter. I place the letters 2 by 2. I reverse the letters of each couple. And I take the first letter. So now I pass to phase 2 and find logs, bioinformatic problems 2, medium difficulty. The problem is to write an APL function which takes an integer vector representing L, returns an integer vector representing X. X contains numbers x1, x2, x3, and so on, and L is a collection of all possible difference between all possible couple of X. So for example, L1 is x2 minus x1, L2 is x3 minus x2, and so on. And knowing L, we have to find X. So we can see this example in order to having a graphical idea of what the set of differences is. And this is the final function. So firstly, knowing L, we have to understand how many elements X contains. If X contains n elements, then L contains an element for each pair of elements of X. So this is the formula to find the number of elements of X starting from the number of elements of L that we know. So this is in the APL language. And then here I make the cumulative sum. I put a 0 because I suppose that the first element is 0. And I take the first 10 elements. Reversal distance. Bioinformatic problem 3, high difficulty. One of the most studied problems in the field of computational biology is the string matching problem. Why? When trying to understand how genetic sequences mutate at the chromosome level, we need to consider more global operations rather than the basic ones. One of the most common global mutation is the reversing of a substring, operation also known as a reversal. In order to represent the sequence of genes on a chromosome, we are going to use permutations. More clearly, we are given the order of n genes in two related organisms. We only consider the genes that appear in both organisms. The order of the genes are represented by a permutation, sigma, whereby sigma I we denote the position where the gene I appears. So, a reversal of a permutation creates a new permutation by inverting some interval of the permutation. So, for example, 5, 2, 3, 1, 4, 5, 3, 4, 1, 2, and 4, 1, 2, 3, 5 are all reversal of 5, 3, 2, 1, 4. The first difficulty was understanding what a reversal is. In fact, on Rosalind's website, there was not a definition, but an example. So I have examined the document Sorting by Reversal by Bogdan Pazaniuk. A reversal is a transformation that, taking a vector of 10 elements from 1 to 10, creates a second permutation according to the following criterion. So a reversal is a function that, taking the interval from I to j, make the reverse of this interval, that so became from j to I, while the other number of the vector that are not contained in the interval remain the same. So the function that makes the reversal is this, and here this is the part that I want to modify, I, and here I modify the interested part, so I, with this reverse. So we are using the APL function reverse. So applied to our example, it is this, where 4 and 9 is the interval that I want to modify. Let's talk about the problem. The problem is to find the minimum number of reversals needed to transform one string into another, so the distance between two permutations. In fact, the minimum number of reversals used to transform one string into another has proven to be a very good estimate for the evolutionary distance between organisms. So the first fundamental idea is that solving this problem is exactly the same of solving this one, where the left argument is increasingly ordered. And this is helpful because now the left string is ordered, and it is easier to pass from one permutation to another. And we change element of x by putting instead of each element the position that this number has in epsilon. So for example, I put instead 5 because 5 is in the 5th position in epsilon. I put instead 2, 4 because 2 is in the 4th position, and so on. At this point, we have to understand how to solve the problem. In other words, we have to understand how to pass from a disordered permutation like 5, 4, 1, 8, 7, 6, 2, 3, 9 to the order 10, to the order 1. First of all, we add the two fictitious numbers at the beginning and at the end, so we force in some way permutation to be increasing. A breakpoint of a permutation, sigma, is a pair of adjacent positions, I and I plus 1, such that sigma of I and sigma of I plus 1 are consecutively decreasing or increasing. The function that calculates the number of breakpoints is this. So it adds a number at the end, it makes the modulo of the difference between each number and its following, and it counts the 1. So here the breakpoints are 5, and we have to use a reversal that improves the total number of breakpoints. And in this way we have 6 breakpoints. The idea is to improve each time the number of breakpoints until we arrive to 10. And so this is a greedy algorithm. And so at each step we try to maximize the number of breakpoints. So this is the final function, where it makes all the possible reversal by using R, so the reverse, and all that find all the couple in which the first element is lower than the second. And then it orders the reversal, putting at the beginning the ones with the highest number of breakpoints, and takes the first one. And I repeat it until we have 10 breakpoints. Longest step sequences. Bioinformatic problem 3, high difficulty. Write an APL function which takes an integer permutation vector of length n, returns a two-element vector where the first one is the longest increasing subsequence of the permutation vector, and the second one is a longest decreasing subsequence of the permutation vector. So for example, if I have the vector 5, 1, 4, 2, 3, the increasing substring is 1, 2, 3, and the decreasing one is 5, 4, 2. So we have to find the increasing and the decreasing subsequences of the permutation vector. However, finding the increasing one is the same of finding the decreasing one, because if we change sign at each number and we find the increasing subsequence, then we change again the sign, we find the decreasing subsequence. But how can I find the increasing subsequence? We can focus on the last number, 3 and search the subsequences that contain 3 as the last element. In this case, 1, 3 and 1, 2, 3, where the longest is the second one. However, it's easier to start from the beginning and go ahead with dynamic programming by searching for each number all the previous numbers lower than the number itself. So if I consider 1, I can't put nothing before because 1 is lower than 5. I put before 4, 1. I put before 2, 1. And I put before 3, 1 and 2. So I take this one because it's the longest one. So this is the final function. It makes the initial matrix and it finds the longest subsequence. So I start from the second item because, of course, before the first one item I can put nothing. And it finds all the indices lower than the number I'm considering. And if there is at least one j, it updates the matrix. And it takes the longest subsequence. HTML table, applications problem 1, low difficulty. The task is to write an APL function that takes a matrix of data as its right argument, returns a character vector of HTML to render the matrix as an HTML table. So this should be the result. So the first operation we do is to put a td before and a /td after each cell of the matrix. Now we pack the lines by putting a tr before and a /tr after. Then we pack the entire table. And finally we clean the nested data. And we obtain this final function. Can. Recreation and games problem 3, high difficulty. Your task is to write a program which will solve a can puzzle. The program takes a 3-column matrix right argument, where column 1 contains the integer target number, column 3 contains a character scalar representing the operation, column 3 contains a vector of cell coordinates that make up the cage, returns an integer matrix representing the solution to the puzzle. So solving this problem consists in solving a Sudoku, and the solution starts from the technique taught by John Scholes, presented in the YouTube video A Sudoku Solver in APL. However, this technique solves a generical Sudoku, while we have to solve a can. So the problem of a can is the fact that there is a strong condition on each cage. And there is a target number, there is an operation, and there are involved cells that cell has the dimension of the cage. The first problem is, can I write a function, the fill cage, which tries to fill with numbers the indicated cells so that they respect the conditions? So the embryonic function of this solution is the fill cage, which has as input n, dimension of can, t, integer target number, o, operation, v, vector of cells coordinates that make up the cage. And the output is the matrix filled only in the cells indicated by the input. So let's see the fill cage. Above is shown the structure of the argument. As you can see, the third element of the vector is a vector that contains the coordinates of the cells to fill, and this makes the input a nested vector. Also, the output is a vector of matrices, so it's nested too. As you can see, there are solutions that are not correct, for example, the first one and the second one, because there is the same number on the same column or on the same row. But we are going to remove them with the sum function in the can function. So I explore all the possible combinations. I check where the combinations are equal to the target number, in this case 16. And I discover the coordinates of the cube, where there is 16 using where function. And in this way I find the set of number whose product is 16. After we have found the possible solutions, we can place them into the matrix with the function at. So it makes the matrix, and it places the numbers omega in the cells alpha. So this is the final field cage. I make all the possible combinations, and I take the coordinates of the cells with numbers that make the target number. Now I repeat this process for the second cage, and I obtain 8 possibilities. So in total they are 16, among which I can take only the ones that don't have the same number repeated on a row or a column. So I have to define a sum function that doesn't accept repetitions. So it makes all the combination of the sum of 2 cages. It controls that there aren't 2 numbers repeated on the same row. And it applies f on the transpose of A, so makes the test also on the columns. And I repeat this process for each cage, and I find the final solution. So this is the final function, where n is the dimension of can-can. So we are using sum and, of course, the field cage. Identifying maximal repeats. Bioinformatics problem 3, high difficulty. The task is to write an APL function which takes a character vector representing a DNA string, returns a vector of character vectors containing all maximal repeats in the DNA string, having a length greater or equal to 20. In order to simplify the problem, I considered a short string used as an example by the Rosalind website. So I took the DNA string TAG, TTAG, CGAGA, in which I have to find a 2 long substring, not a 20 long one, and this economizes everything. So the problem is divided into points. In fact, I have to find all the substring which repeat, so there must be at least 2 of them, and are not extensible, because I have to find the maximal substring, the longest repeated one. So, for example, AG is a maximal repeat in the DNA substring, because even though the first 2 occurrences of AG can be extended left into TAG, here and here, the first and the third occurrences differ on both sides of the repeat. Thus, we conclude that AG is a maximal repeat. Note that TAG is also a maximal repeat of the string of the DNA, since its only 2 occurrences do not seal match if we extend them in either direction. The idea I followed is the Croque-Moore algorithm, because it perfectly combines with the APL function find. So, for each letter of the DNA, I considered how it can be extended. I obtain the substrings of length 2, and I try to extend them, and I go on with this process until I obtain the longest repeated substring. This algorithm seems slow, but it's not like that. So with this function, I search where the letters A, C, G, T are in the DNA string, and at the beginning this is the result. And this is the first turn. Now A and M coincide, but M will remain the same while A will evolve. Now I try to extend the substrings by creating that of 2 elements in this way. So I find I find the positions of the couples, and I find the repeated strings and their positions. So AG, GA, TA. I go on with this process to find the substrings of 3 letters, and only TAG survive because we have found it twice. So this is the final function. It finds the positions of the repeated substring. It finds the repeated substrings. It removes the shorter substrings that are contained in the longer substring that I found using G that I'll explain in the next slide. And it puts together the obtained results. Finally, it reverses the results to put at the beginning the most repeated substring. So this is G that we use to clean the result I've just obtained from the result I obtained before. So it searches which substrings, for example, of 2 elements are contained in that of 3 elements. It controls if the shorter substring occurs the same number of times as the longer substring in which it is contained. And it removes the shorter substring that are always contained in the longer one. 2048, Task 1 and Task 2. Recreational and game problems 2, medium difficulty. These problems are based on the game 2048, first implemented on the web during March 2014 by Gabriele Cirulli. At start of the game, 2 random cells of 4x4 grid are assigned a value of 2. The user has to indicate a direction, up, down, left, right, to size the cells and the cell slide as far as possible in the chosen direction until they are stopped by another cell or the edge of the grid. If 2 cells of the same number collide, they will merge into a cell with the total value of the 2 cells that collide. For example, if I have 2, 4, 4, 4, and I make the shift to the right, I obtain 0, 2, 4, and 8. Task 1, Shifty thinking. The task is to write a function, shift2048, which takes a right argument, which is a 4-element integer vector representing 4 cells, well, 0 indicates a blank cell, and takes a Boolean scalar left argument, which indicates the direction to shift, 1 for shift to the right, 0 for shift to the left. Returns a 4-element integer vector representing the result after the shift. For example, if I have 2, 4, 4, 8 and I make the shift to the right, I obtain 0, 2, 8, 8, while if I make the shift to the left, I obtain 2, 8, 8, 0. So our function will work in this way. In fact, not only it will return the vector, but also the sum, 8, and this will be useful for the second part of the problem. The main idea of the function is that if I find a way to shift to the left, I will be able to shift to the right too. This simplifies everything because I can do all the reasonings at once. I explain better. If I have 2, 4, 4, 8 and I make the shift to the right, I obtain 0, 2, 8, 8. If I reverse the starting vector, I obtain the 8, 4, 4, 2. If I make the shift to the left, I obtain 8, 8, 2, 0. I reverse again, and the result is the same, 0, 2, 8, 8. So, this is the logic of the solution. I call this is x. I make the shift to the left. It takes the couple of equal numbers, and it becomes a. It makes the sum of x and a times x. It makes the shift to the right of a, and it becomes b. It denies b, and it adapts b on z, and it adds a 0 at the end. Finally, I add the sum 8. So this is the final function where these are the passages I've just explained. So task 2, all a board. Now the problem becomes 2-dimensional because there is a board. But if we imagine the single rows of the board as vectors and we apply the shift to each row, it is clear that applying the shift to the matrix is equivalent to apply it to each row. So the 2 vertical shifts, up and down, added to the horizontal ones, left and right. And also the vertical shifts can be traced on the horizontal shift after rotating the matrix and the result. So if this is the current matrix and I make the upshift, I obtain this result. But if I make the transpose of the starting matrix and I make the shift to the left, I obtain the result. I make the transpose again of this result, and the final result is the same. So this is the final function. I turn the matrix into a vector of rows and apply shift 2048, then I make the matrix again. If the shift is vertical, I rotate the matrix, and I put the sum next to the matrix. In fact, when the matrix rotates, even the sum rotates. And here I make the sum of sums of all rows, and I put the sum next to the matrix and I remove the last column, so the column where there was the sum of each row. Arrange stars. Applications problem 3, high difficulty. Imagine that a new state is admitted to United States. How could the USA's flag change? Given a number of stars, we have to choose a new harmonious arrangement of the stars. So the problem is to understand what harmonious means. To solve this problem, we relied on the work of Skip Garibaldi, American mathematician, who defined all the possible patterns to arrange the stars. So Wyoming pattern single, Wyoming pattern double, short-long pattern, long-short pattern, alternate long-short, and equal. So this is the Wyoming pattern single, with a single line shorter in the center. This is Wyoming pattern double, with 2 shorter lines in the center. This is short-long pattern with short and long lines alternated. Long-short pattern with long and short lines alternated. And finally, equal. Another important resource to solve this problem is the widget NextPickFuture that allows you to have a graphical image of the modified fledge. This is useful in particular to control if the solution obtained is correct. Here there is the, if I put, for example, 48, this is the pattern, 47, this is the pattern, 46, and so on. Okay. But let's see the details of the problem. The task is to write a function that takes a right argument integer singleton representing the number of stars to place, returns a 3-item vector describing a reasonable star arrangement, where the first item is a vector of the number of stars in each row, the second item is the horizontal spacing between columns of stars, and the third item is the vertical spacing in between rows of stars. We have to assume that the ratio of A to base is 1 to 1.4. So, for example, if my input is 10, the output will be 3232, so number of stars in each row, 0.2333 horizontal spacing, and 0.2 the vertical spacing. However, the second and the third elements of the output are derivable from the first one, and this can be easily understood by watching a drawing. So, if the base is 1.4, h will be 1.4 divided by 6, and if the height is 1, f will be 1 divided by 5. So if my output is 3232, the number of columns is 3, and the horizontal space is 1.4 divided by 6, so divided by 2 times c. While the number of rows is 4, and the vertical space is 1 divided by 5, so divided by r plus 1. In this way, we have found that h is always 1.4 divided by 2 times c, and f is always 1 divided by r plus 1. So the function of alternate long-short pattern is this, where it gives me the first element, so the number of stars in each row, where alpha rho omega is the long row and alpha rho omega minus 1 is the short row. It gives me the second element, so the horizontal spacing between columns of stars, and it gives me the third element, so the vertical spacing between rows of stars. However, our input is not a couple, R and C, but a number, for example, 22. And by starting from 22, we can only say that R and C must be between 1 and 22, and that R must be even. So I have 11 possibilities for R and 22 possibilities for C. And we have to examine all the possible couple of R and C to reject those that are not correct. For example, 4 rows and 7 columns, because it will be 7, 6, 7, 6, but the sum of stars is not 22. And in this particular example, the only possible arrangement is 6, 5, 6, 5. However, we have considered only one pattern, alternating long-short, and so we have to repeat the reasoning for the other pattern and see if there are other possible arrangements. In this case, there are 15 possible layouts, and these are some of them. So 11, 11, 6, 5, 5, 6, 4, 4, 3, 3, 4, 4, and 3, 3, 3, 2, 2, 3. But how can I decide which of them is the best? The best is the one in which the difference between H and F is minimal, because in this way the stars will be bigger and the arrangement will be harmonious. So this is the final function. Here there are the functions for each pattern, so equal, long, short, short, long. Alternate long, short is a particular case of long, short with even rows. Wyoming single and Wyoming double. Here I apply all the patterns, and I take all the patterns in which the sum of stars is equal to x, and I take the one in which the difference between horizontal and vertical space is minimum. Now I've finished, but I'd like to make a final note. Since I had the opportunity to take part into the contest thanks to the free course held by Minervini, I think it is right to donate the prize I won to schools, so to invest the money to finance a course of APL language, of course, so that other students will be able to have the same opportunity I had.